continued with the topic of floating point arithmetic, and there we looked at addition, subtractions, so floating point adders, and multiplication. So multiplication is an easier task because you don't have to make the exponents equal, uh, and you just have to multiply and add the exponent values, or in division you just have to divide and then subtract the exponent values. So it's an easier task than addition, subtraction. So an adder, for a floating point adder, takes uh, many steps to complete the addition process, and we discussed about that in the last class. Then we came to the next topic, which was instruction level parallelism. We are going to continue with that topic in this class as well. So we started with the concept of pipelining. When you're talking about instruction level parallelism, we are talking about having more than one instruction, running more than one instruction at a time. So there is some overlap between instructions. So it's not about running all the instructions in parallel. It's about doing that in an overlapped way, such that you don't use a lot of resources. So what you'd have is your existing resources are divided in such a way that you break them into stages, and when you break them into stages, you also prevent the stages from communicating with each other using some registers. And this allows you to have one instruction per stage, and when that stage is complete, when the task is complete for that particular stage, then it's moved on to the next stage, and so a new instruction can come along. So in the next cycle there are 2 instructions, in the next cycle there are going to be 3 instructions, and so on, right? So if you have got 5 stages in your pipeline, then it will take some time, like 5 cycles, to fill that pipeline. But afterwards, you're going to see that the instructions are going to come in and leave the pipeline after just 1 cycle. So they are going to take the same 5 cycle time. But what we do over here is we have an overlap of 4 cycles with our previous instruction. And so the effective delay, the effective time that a new instruction is going to take is just going to be 1 cycle. So this is how you increase the throughput, and you complete more instructions in a unit time, right? So we discussed about, so in order to understand instruction pipelining, you should have some architecture in your mind, some architecture that you are going to discuss. So we discussed about a MIPS processor. It's a simple processor having, it's a RISC-based design. So you all are familiar with reduced instruction set computers. In a RISC-based design, what happens is you have simple instructions and simple addressing modes. So these instructions are not complicated. So what happens is that if you're going to write some program, it's going to take more instructions to write program. But if you look at the architecture, it's quite simple internally, and it's going to take more instructions to run the program, but it doesn't mean that it's going to take more time. Because these instructions are simple, they take less time, and then you execute more instruction, but the timing is a little complicated thing over here when you talk about RISC, comparing RISC with CISC processor. So the other processor is a CISC-based processor. They have complicated instructions, so they have instructions that do a lot of tasks in just one instruction. And when you're going to program, when you're going to design for an architecture, keeping in mind that you have got a very complicated instructions, the architecture gets very complicated as well. So the control unit design gets complicated, the addressing modes are more, and then you need more control signals to complete that instruction. So there are two different architectures, the RISC-based architecture and the CISC-based architecture. In order to understand pipelining, it's better if you go with RISC-based architecture. So we decided to go with MIPS pipeline. We could have also have selected a RISC-V processor. RISC-V is a continuation of the RISC processors that were designed at Princeton. So MIPS were designed at Stanford, and RISC were designed at Princeton University. And these processors almost have the same design as MIPS processor, but they have some different instruction formats. but I'm not going to discuss about RISC-V. But RISC-V is quite famous these days because different companies are working on it. They are working on different variations of RISC-V because it's an open source. And if you look at your mobile phones, most of the time, I mean 95% of these mobile phones have an ARM-based processor. So the ARM market, the mobile market has been captured by ARM processor, just like the desktop PC market has been captured by Intel processors. So what's happening here when you're talking about ARM processor? If you want to build a chip for mobile phone, you have to buy those designs, and these are intellectual properties of ARM systems. So they are going to give you the code for that processor, and then you can obviously build something on it or customize that, but you have to pay for that. When you're talking about open source, then you get these things for free. What is the advantage of having open source? One of the advantage here is that just like Linux, that if people have got these open source, then they are going to work more on that, and if they are going to build more using that. So many of the companies are coming to RISC-V processor. So it's a simpler design. I didn't select it. I didn't select RISC-V just because the books available in Pakistan are very few related to RISC-V. So if you're looking at computer architecture quantitative approach, the books that we are following, the fifth edition is available in Pakistan, and they have given the examples using MIPS processor. But if you're talking about the sixth edition of that same book, then you're going to see that in the sixth edition they have talked about the RISC-V processor. The examples are not very different. Again, the RISC-V processor that they have considered is also having 5 stages and the similar stages, except that they have a different instruction format. There is not much of a difference between these two processors if you're considering the examples from the book. Obviously, in RISC-V, then they are different. You can add more instruction. You can add your own instructions as well. So that's a little different issue. We are not going to come to that. So we started with the MIPS processor, and we said that there are going to be 5 stages in our instruction cycle, and these stages are going to be instruction fetch. And in that stage, you're going to fetch the instructions. So you just get 32 bits from memory. Then you go for the decoding stage. Now, in the decode stage, you do 2 things, and these things can be overlapped, but we are going to see if they are overlapped from the beginning, then what are the problems that can come. So in the decode stage, we do 2 things. We decode the instruction, the 32 bits that we have fetched, and then we also read the registers. Now, normally what's happening in an instruction cycle is once you have decoded the instruction, then you know whether or not to read the registers. Most of the time, you have to read 2 registers, and sometimes you just have to read 1 source register. And yes, there are no instructions in an instruction set architecture which is not going to read any register. If you have store instruction, that's also going to read register. If you have branch instruction, that also reads register. So all the instructions read register. So normally what happens is that after decoding, we get to know which registers, how many registers to read, 2 or 1. But if you're doing both of these tasks in a single stage, what happens is that you have to make this stage common for all the instructions. So if you're going to make that stage common for all the instructions, this means you are going to read 2 registers for all the instructions, irrespective of whether they need just 1 register to be read. So for example, if you have got a load instruction, which is, I'm going to come to the load instruction. So if I'm going to write a load instruction, it would be something like, there are 2 variations. I can have a load double as well, or a load word, which is going to load a single 32-bit integer. Load double is going to go for a 64-bit floating point number. In load double, I'll be focusing on 64-bit registers or maybe floating point registers. In load word, it's the common registers. So I'm going to take the example of load word, for example. So if you have got load word, and if I write an instruction like load word R1 100 R2, Now, how I'm going to interpret this instruction? So what's going to happen is this part here, the 100R2, is actually the address. This is the address of the memory, right? So in memory, there is something which is stored at this location, and I need to fetch that particular element from memory, and then I'm going to load it into R1. So R1 is my source register. Sorry, R1 is my destination register, and R2 is my source register. So you can see here there is just a single source register. Now, if I give you an example of, say, an add instruction, then an add instruction would have a single destination register and two source registers. So if I write add R1, R2, R3, that will add R2 and R3 and then store that result into R1. Okay, so a load is a little different than this. So in load, you're going to load it from memory, and then you're going to store it in R1. And here, you are going to add these two registers and store it in R1. So you can see here what I wanted to say was that sometimes you have got two source registers, sometimes you have got just one source register and some immediate values, right? But reading of register is going to happen in the decode stage. If you look at the instructions, these are the instructions that I've written in assembly form. But if you look at the instruction format that we discussed in the last class, so their instruction formats are going to be a little different. Now, they both are going to have opcode at the same position. So they are going to have opcode in the starting, or you can say in the most significant 6 bits. But then there are going to be 3 different register codes in an add instruction that would be named as RS, RT, and RD. D for destination here. But here we just have 2 register codes. And they are, to keep the instruction format similar, they are RS and RT only. And the remaining field is for the immediate value, like 100 that you are storing over here. So 100 would be stored over here. Now RS, so this is the source register code, and RT is also normally the second source register code, but we don't have any source register code, rather we have a destination register code. So this RT here is going to work as a destination register code. So we are going to store the value or the code of R1 at this point, and this R2 code is going to be stored over here. This 100 is going to be stored over here, and the opcode would be for the load, and this then completes the instruction here. So this is one example of load. Now in the store, what's going to happen is R1 is going to be, R1 is the destination, right? And R2 and R3 are going to be sources. So RS would be R2 and RT would be R3, right? So what I wanted to say was in a load instruction, there are no 2 source registers, but since in the decode stage we have to read the registers irrespective of what instruction it is. So what we are going to do, since these are the 2 fields for the source register, we are going to read both of them in any instruction. So in any instruction which is in the decode stage, you are going to take these 2 register codes and give those register codes to the register file, and you're going to read 2 values. If you need that value, you're going to take that to the next stage. If you don't need that value, in the next stage you are not going to use that. So what's going to happen here is you are going to read R1's value in the decode stage while you don't need that value here. You don't need to read value over here because you have to store something into it. You don't need that value to be read in the second stage. But to make everything common in the second stage, to make all these operations common for all the instructions, we are going to read R1's value over here. But in the next stage, we are not going to use that. And so eventually in the last stage, we are going to override the value of R1 with something that has been fetched from memory. So this is what I wanted to say, that in the decode stage, what's going to happen is you are going to read the register contents as well. And then the third stage is the execution stage. In the execution stage, we actually perform that data, that operation. For example, if it's an add instruction, we are going to add. If it's a load instruction, we are going to calculate the address. Calculate the address means that 100 plus the contents of R2 would be added, and that would become our the address of data. And then in the memory stage, so the memory stage is the fourth stage, which is used only by two instructions, two types of instruction: the load instructions and the store instruction. Now in the RISC processor, what happens is that you simplify the design. So you only allow operations between registers. You don't allow operations between memory and register operands. So in order to have some operation between memory and a register, what you do is you bring down those memory elements first into some register and do then a register operation. So since MIPS is a RISC processor, so this memory stage is only utilized by, sorry, this memory stage is only utilized by um, two instructions: the load instruction and the store instruction. So only two types of instruction here: the load instruction and the store instruction. Uh, okay, the load instruction and the store instruction are going to use the memory stage. So what about the other instructions, like arithmetic instructions? So they are not going to use this stage, but still they have to pass through that stage. We're going to come to that. And the last stage was write back stage, where you're going to store the result in some register. Now in a store instruction, you're going to store the result in the memory, and there is nothing more required in the store instruction. But for all the other instructions, you have to store the result in some register, except store and branch instruction. So what's important here is every instruction has to go through all these 5 stages. So if the store does not need the last stage, it still has to go through that stage. If the add does not need the memory stage, it still has to go through the memory stage, right? So this makes the things simpler. Now what happens if you are running your programs and there are instructions coming one after another, and the pipeline that we have discussed with 5 stages is that you start a new instruction from a new cycle, and then it's going to take 5 cycles and it's going to complete. So you're going to see that after 5 cycles, you're going to see that since a new instruction has started from a new cycle, so every cycle after the 5th cycle is going to finish one more instruction. Sometimes this does not happen. Sometimes there are problems in the pipeline. Now, when there are problems in the pipeline and you cannot start a new instruction from a new cycle, we call those events as pipeline hazards. Now, pipeline hazard is described as a situation that prevents an instruction from using a pipeline stage during the designated clock cycles. And there are 3 types of hazards: structural hazards, data hazards, and control hazards. So when we talk about structural hazards, as the name specifies, structure or hardware. So these hazards are because of insufficient hardware resources. So if your hardware resources are not sufficient and you don't have enough resources to run the combination of instructions together, then you have to stop one of the instruction and to let go the other one. So the instruction which has been stopped is obviously going to lose cycle, so it's not going to start from its right position, right cycle. So that's what we call as a structural hazard, right? So if the hardware cannot support your pipeline behavior, that you can start a new instruction from a new cycle, so if the cause of that is the hardware issue, then we are going to call that as a structural hazard. Is there a question here? I'll say Heather, your mic is open. So is there a question? Okay. Then we have the data hazard. So when talking about data hazard, It's because that the data is not available. And I'm going to come to the examples of each of these shortly. So if you want to run an instruction and it's dependent on any of the previous instruction which has not completed its result, and the result is not written to the register, then you can obviously not start a new instruction. So if that is going to prevent you from starting the instruction from its right time, the right cycle, then that's called as a data hazard. So in structural hazard, the hardware was the issue. In data hazards, the data is not available. And the third hazard is the control hazard, where it's because of the branch instruction. And when you have the branch instructions, you usually change the flow of your program. So you jump from one position to another position. But when you're talking about pipeline, what happens is that you always fetch the next sequential instruction, right? But branches are going to jump to a new position. So if there are branches and they are taken branches, that is, they have to jump, then you're going to read the sequential instruction and do some execution on those sequential instructions. But later on, you're going to find out that you shouldn't have executed, you shouldn't have fetched those instructions. So and you have to fetch a new instruction from some other place. So those instructions which are in the pipeline have to be removed from the pipeline, and obviously in that case also you're going to lose some cycles. So in all these three cases, we are unable to start the new instruction from a new cycle, right? So I'm going to start with structural hazard and give some example on that. Right. So let's concentrate on this diagram over here on the right. So if you see over here, we have a sequence of instructions in the pipeline, and here the pipeline's hardware modules are shown in a replicated way. That is, we are replicating the same modules again and again to illustrate which particular module is using which particular stage, which particular instruction is using which particular stage. And each of these stages is not numbered or not named as IF or ID, but rather we are going to describe what is the particular hardware module that stage is utilizing. So for example, the first instruction is the load instruction. Now this is a sequence where we have our first instruction as a load instruction, right? And you have your next instruction. That can be any other instruction in the cycle number one. So this is your first cycle. In your first cycle, load is going to be in the first stage, which is the fetch stage. And since fetch is going to work on memory, so we have written here memory, right? Now in the second cycle, what will happen is the load is going to move to the decode stage. And as I mentioned, in the decode, we are going to decode the instruction as well as read the registers, right? So since decoder is something which is internal to the processor and is used only once in a particular instruction, so I have not shown the decode over here. So the main module that we are concentrating here is the register file, which would be utilized to read the registers. So you can see here in the second cycle, what will happen is, so in the second cycle, what's happening here is the first instruction is going to use the register file, and the next instruction, the next to the load instruction, is going to use the memory for its fetching, right? So next instruction is going to be fetched in the second cycle, and the first instruction is going to go to the decode stage where it's going to read the registers. So no problem over here as well, because there are two different hardware modules, and both of them can move along in the same cycle. Now let's move to the third cycle. Now load will calculate the address using the ALU. Instruction 1 is going to move to read the registers and is going to use the register file. And instruction 2 is then going to use the memory. Again, no problem over here, because all of these three are different hardware resources. So nothing here in cycle number 3 as well. right? Now, if you move to the fourth cycle, now in the fourth cycle, load is going to go to the memory stage, which is going to utilize memory. Instruction one is going to move to the execution stage where it's going to perform execution using ALU. Instruction two is going to read, is going to go to the decode stage where its registers would be read. And then we have instruction three, which is going to be fetched. Now, if you look over here in cycle number four, there are two things, there are two instructions which are using using the same hardware resource. So we have a memory over here and a memory over here. And that's the same cycle, cycle four. Now, here comes the problem here. Now, as I mentioned here, that structural hazards are because of hardware resources, the conflicts in hardware resources. Now, in the same cycle, memory is used twice. If you have a memory with you which allows you to give an address for a particular location and it's going to return back some data, then you cannot use that memory for two different operations in the same cycle. Now, this is the first case of structural hazard, right? So there is a conflict over here. So both these instructions cannot move at the same time, right? So both these instructions are utilizing load instruction, and the third instruction is are utilizing the memory module. And if the memory module is such that it's going to allow either a single read or write, then you cannot have both of these at the same time. Okay. Now, what can be a solution for this? Obviously, we cannot start both these we cannot have both these instructions running at the same time, cycle number four. So since load was initiated in cycle number one, we could allow this to propagate through the memory stage, and then obviously we have to do something for instruction number three. So what we do is we stall it. And when we say we stall it, means that we are going to add a delay of one cycle. So its write time was cycle number four, but we are not going to start this from cycle number four. We are going to delay this, leave cycle number four for the fetch leave cycle number four. There is going to be no fetch operation happening in cycle number four, and we are going to fetch instruction number three from cycle number five. So this would mean instruction four is also delayed, and anything after instruction three is also delayed. So instruction three now starts on cycle number five. Instruction four now starts on cycle number six, right? Now, the effect of this delay is that you are not going to complete any instruction in cycle number eight. So since you have started cycle instruction number three from cycle number five, you are going to end instruction number three in cycle number nine. And there is no instruction completing cycle number eight, and you have wasted one cycle, right? So whenever there are hazards, there is a possibility that you are going to insert stalls, and inserting stall means that the CPI or cycles per instruction are going to increase, right? So we define CPI as the cycles per instructions. So how many cycle is one instruction taking? If you look at the diagram over here for a pipeline, normally what happens is the ideal CPI for a pipeline is 1, because you need that every instruction take just one cycle. So just leave the initial stages where you're going to fill the pipeline, but later on, if you have got many instructions, then you just ignore the initial few instructions. So what we say is the ideal pipeline CPI is 1. But if you're going
Sir,
to
sir, what is the limit of the cycles? Cycles are infinite, or is there any limit of cycles?
right, so the first thing that we discussed in the last lecture was an instruction cycle is going to do many tasks, right? And these tasks can be divided into different stages. Now it's up to you how many stages do you want, right? The main thing that you have to consider is when you're going to divide the big instruction cycle into different stages, you have to consider that all these stages take equal duration of time. Because if they are going to take unequal duration of times, then your clock cycle time has to consider the slowest stage. And when it considers the slowest stage in determining cycle time, then the overall advantage of having pipeline is reduced. So if you're going to divide this instruction cycle into stages, you divide them considering that they are of equal duration, right? So what we did in our example is we divided it into 5 cycles or 5 stages. 5 stages, each stage taking 1 cycle, right? So here in our example, an instruction is going to take just 5 cycles. But had we divided our instruction cycle into 8 stages, we would have needed 8 cycles to complete the same task. Those cycles would have been smaller than these cycles, but they would be still considered in terms of cycles. I hope that answers your question. So in this example, we are going to talk about just 5 cycles. And it depends, if you are asking how many cycles are we going to talk about, it depends on the program. It's going to take many thousands of millions of cycles, so we cannot show all of these cycles. So it's just an example over here. Is your question answered?
Okay, sir.
Yeah, sir.
Yes, sir.
Okay. So
One thing more, sir, that here memory functions are different in of load and instruction tree. That's why
okay,
you have
yeah.
add
I'm going to
instruction.
come. I'm going to come to that. Right. You have detected the problem correctly. Uh, uh, they are different memory functions in the same cycle. I'm going to
Yeah,
come to
if
that.
yeah, if same, then what will happen? Whether it will be further proceed to instruction 4, or will it be prompt to error or not?
Okay. So, all right. So this is a structural hazard, and a way out for a structural hazard is to um, a way out for that is to stall the pipeline. Now, stalling anything means that you're going to waste cycles, so you don't need to really stall the cycle. So you should come up with some different solution for that. Now, if this is my shared memory, and this memory is utilized by the CPU for its operations. So normally this memory is shared, and it's going to hold both the instruction part and the data part. So we differentiate instructions and data because instructions are the instructions or the code of your program, and data is the elements on which you are going to work. So for example, if I have add R1, R2, R3, that is an instruction written somewhere over here, but the data for R1 and R2, maybe if it's coming from memory, has to come from some part over here and stored in some register, and I'm going to work on that data, right? So instruction is the code, and data are the elements on which you are working. So when you're talking about memory, there is no fixed position for instruction or data. So you have them mixed up, or you can say there is no limit to how big your instruction program can be, or how big your data elements can be. So normally there is no limit. So you can store them in different ways and different positions in memory. So you cannot differentiate that this thing is an instruction and this thing is data just by looking at the address of the memory address, right? So CPU is going to generate an address, and there are two things happening at the same time. Both these operations are going to generate addresses. So load is going to generate an address, and instruction 3 is also going to generate an address. But what's happening over here is we just have a single memory over here. Sorry, where is that? So we just have a single memory over here, and CPU cannot generate two addresses at one time. Right. So one way is to stall it. Now, if you're going to stall it, what's going to happen? Now, if I stall this thing, that is instruction 3 is going to start in cycle number 5. Okay. So instruction 3 starts in cycle number 5. Nothing happens over here. So this thing moves on. But if you come to instruction number 5, again you're going to see there is a memory over here, and then there is a memory over here. So again there is a problem. Now if this instruction 1 is not a load or store instruction, then again it can move, because this memory stage is utilized only by load and store instruction. That's why we had load as our first instruction, because we wanted to use this memory stage. So if instruction 1 is anything other than load and store, then obviously you can start instruction number 3 from, so nothing's happening over here, and this thing changed to instruction 3. So if instruction 1 is not load and store, so if it's not load and store, then you can start instruction 3 from cycle number 5, because this memory stage is not going to be utilized, and so you can fetch your instruction 3. But if this is also a load instruction, if instruction 1 is also a load instruction, then again you have to insert another stall of 1 cycle and start instruction 3 from cycle number 6. So this means you have wasted 2 cycles, and any wastage of cycle is going to increase the CPI, right? So this is a problem over here. So we just can't keep on adding more and more stall cycles. So we need to have some good solutions for this, good solution for that. So if I come back to my example over here, now what's happening here is, in a single cycle you cannot generate two addresses at the same time. So a way out could be to have two different memories. Instead of a single shared memory, you can have two different memories. Like we can have an instruction memory and a data memory. Normally they are not called as instruction memory or data memory. They are normally called as instruction caches and data caches, right? So what happens is, we have a level of memory, and that's a faster memory, and we have a different way of accessing those memories, and we call them as caches, right? I'm going to come to that as well later, when we are going to discuss memories. So if we have two different memories, then and all the instructions are going to the instruction cache, and all the data elements are going to data cache, then the CPU can generate two different addresses at the same time, right? So this can happen the same cycle. This can happen the same cycle. Remember what has happened, what was the problem, and what has happened now. The problem was that we had a single memory. That was a hardware issue, so we could not execute two different instructions at the same time. So what the solution for that is to have two different physical memories. All the instructions go to this memory, and all the data elements go to this memory. And if that is the case, you can then have both these operations simultaneously. Now the only problem left is, how am I going to populate instructions in the instruction memory and data in the data memory? Now the CPU is going to look for instructions over here, but since this won't be full for the first time, or when the power system is powered on, so it's going to be a mess over here, and then the CPU is going to access the main memory for the instruction. So the question is that CPU is going to generate, whenever the CPU is going to generate an address for the memory, how would the memory know to put that data element in the instruction memory, or put that data element in the data memory? How would the memory or some other module, a memory management unit, would know that that particular address is for instruction or is it for data? Can anyone answer that? The question is that initially these caches would be empty, and if you're going to generate an address, then you are going to go for the shared memory. And if you're going to generate an address, the memory is going to return some data. How are we going to populate these memories? How are we going to put or select a particular memory that this thing is going to go over here and this thing is going to go over here? So for example, if you're talking about this particular case, so if the CPU generates an address in cycle number 4, Is this address for load, or is this address for a fetch operation?
So the opcode will determine this.
Um, Opcode,
Like if it's if it is code,
where is the opcode?
the opcode. If there is an instruction, like if the instruction says that load a certain thing from memory, so
Right.
it will actually data. So the instructions related to data will have a specific opcode. So if the CPU knows that opcode, so it can direct it directly to the data memory.
Now, actually, CPU knows that this is an address of an instruction or this is an address of a data. That's no problem for CPU. The problem is for the memory or the memory management unit. So if that address is generated by CPU, how are we going to put that data into the instruction memory or data memory, right? So now to keep things a little simpler, uh, normally it's not a very difficult question. What happens in CPU is there are different ways to access elements, but there is just a single way to access instruction, and that is the program counter, right? So the program counter is the only register which is holding the instruction address, while data addresses can be stored in any temporary register or any of those registers, or a combination of register plus the immediate value. So this then goes obviously to some kind of a temporary register internal to the processor, and from there on it's going to generate the address. So if your address is coming from program counter, if the program counter is generating the address, then the returned value or returned 32 bits are actually instructions. If any other temporary register is generating the address, then that value is a data value, right? So this is an easy thing to see. So if the program counter is the one which is which is generating the address, which has the address, then it's an instruction, and the data has to the value fetched has to be stored in the instruction memory. Otherwise, it has to be stored in the data memory. Now, this is how you can populate these caches. And once populated, what's going to happen is CPU is going to can perform these two operations simultaneously. So it can generate, so all the program counter values are going to be searched in instruction caches, and the other values are going to be searched over here. So if the value is found, it can be returned to the CPU, and if the value is found over here, it can be returned to the CPU. And both of these tasks can happen in the same cycle, right? So how are we going to handle this issue? So one way is to stall it, and we said that stalling is not a good option because stalling means that we are going to increase the delay, and the procedure of pipelining was used to is used to improve throughput, but stalling is going to reduce the throughput. So this is not a good solution, right? So the other solution is to use a Harvard architecture. A Harvard architecture means that we are going to have separate memory units for instruction and data. So if you have got separate memory units for instruction data, this means that you can have both these operations done in parallel, right? Now, if I come back to the same diagram over here, we did this for cycle number 4. If are there any questions here? So everything is fine for cycle number 4 because now I'm going to change this memory to instruction memory and this memory to data memory. Sorry, I've done that wrong. So this memory is the data memory and this memory is the instruction memory, because we have to fetch the instruction for this. Now you can see here that there are four different hardware resources, and since there are four different hardware resources, there is never a conflict in this case. So cycle number 4 is also fine, right? Now let's come to cycle number 5. So we have discussed cycle number 1, 2, 3, 4 was problematic, but we have overcome that by using Harvard architecture, that is using two different physical modules. And if there are two different modules, then you can generate two different addresses as well from the CPU side, and which are addressed to the two different physical memories. So one of them is going to data memory, and the other one is going to instruction memory, and so we can have both these tasks also happening in parallel. So everywhere where we are fetching, that's going to be changed to instruction memory, right? Now let's come to cycle number 5. Now what's happening in cycle number 5? So this is the data memory, and this is the instruction memory. So nothing is problematic in this case, except that we are using the register file twice in the same cycle. One is for writing the result of load into the particular register, and for instruction number 3, again instruction number 3 is going to read the registers. Okay, so again a hardware conflict, a hardware resource that is common and in the same cycle. So what's going to happen is, normally you have multiple read ports, but only a single write ports, but that reading and writing should happen at different times. Because for example, if you want to read the value of R1 and write the value of R1 at the same time, now that is going to be a problem, because you don't know which one has to be written first and which one has to be read first. So what is the older value? Do you want to write the older value first and then read it, or you want to read first and then write to the older value? So normally what happens is we don't allow read and writes to happen at the same time. So we need to have some kind of sequence that reading should happen first or writing should happen first, right? So in the 5th cycle, we are using the register file for two different operations. We are reading also to the register file, and we are writing to the register file as well. Now, when we discussed in cycle number 4, we said that there were two memory operations, but since the memory operation is a big operation, it's a slow operation, we cannot have two operations coming one after another in the same cycle. Now, that problem is not here if you're talking about registers. Why? Because registers are internal to the processor and they take less amount of time. So if my cycle time is something like say 100 picosecond, and my register reading takes about, say, 40 picoseconds, and writing takes about, say, 50 picoseconds. This is the reading time, and say the writing time is 50 picoseconds. Then I can say that, okay, I can have two different operations in the same cycle, provided I divide that cycle into two halves and manage reads first or write first, any one of them earlier, and the second in the later half of the cycle. Now this is a different way. This is a different way than what we did in the memory, because if our cycle time is 100 picoseconds and memory is taking something like 100 picoseconds, then we cannot have two different operations in the same cycle. But for registers which are taking less time, we can have two different register operations happening at different times in the same cycle. So a way out for that is to divide that cycle into two halves, and then you can manage which operations should happen first, right? So you can then manage which operations should happen first. So what we are going to do here is, each of these cycles are going to be divided into two halves, and in the first half we are going to do any write operation to a register, and in the second half we are going to do any read operations to the register. And there is a reason for that. I'm going to come shortly to that. why are we doing writes first and reads second? We could have started with reads first and writes in the second half, but you're going to come to I'm going to come to that later. Okay, so if we do this, then again there is no hardware conflict, because in the first half you're just writing to a register file and using the register file for only this operation, and this is obviously the data memory, this is ALU, and this is the instruction memory. So again, you're going to see nothing is happening which is common in the first half, and the second half the write operations have completed. So in the second half you're going to release those registers, and then you're just going to read the register contents, right? So again, the register file is used for a single instruction. So this is how again we can remove the structural problems, the structural hazards, right? So we have discussed in structural hazards two different ways to do this. One way is to replicate the resource in such a way that we have different resources, different physical memories. The other way is if your operation is completing in less time, and you can have more than one operations of that same resource in the same cycle. What you do is break your cycle into different parts and do these operations differently at different times, right? But that would be the same cycle, the same fifth cycle, which is going to happen. So writes are going to happen the first half, and reads are going to happen the second half. Okay, so I'm going to take a break over here right now. And if there are any questions, then you can ask me, or we can have that after the break. So I'm going to take a small 10-minute break, and then we are going to join after 10 minutes. So that would be around 7:31, 32, right?
So it means that two register can be accommodated in one cycle, unlike memory.
Yeah, two register operations are going to happen in one cycle, but these register operations are going to be like read or write to a register file. So actually, one operation is happening in the first half, and the other operation is happening in the second half, right? So when we talked about the register file, we said that in the register file you can write data and you can read data from the registers. So, but you cannot do both of them at the same time. So the other approach that we did here is that we have bifurcated our cycle. We have divided a cycle into two halves internally. So that can be done by, if, for example, if this is your cycle, then any writes are going to happen the positive edges, and reads are going to happen the negative edges. So that's
We
how
can
you
do
can
it vice versa. If one is read, then the other one is write. It should be right, and vice versa. We cannot start both with right, I believe.
no, both of them cannot be right. Both of
Otherwise,
them
it will be a conflict.
Yeah, but there will be a conflict. But the thing is that we never have moved more than two write operations for a particular instruction. So an instruction, any instruction here in RISC, is just going to have a single write. That's another issue, that you should also have a single write operation. So in all RISC instructions, you're going to see that there is a single write happening, and that also happens at the very end, right? So if you have got multiple writes, for example, instruction 1 is also writing and instruction 2 is also writing at the same time, that's a problem. And
Now,
that is,
suppose, sir, if here is load and instruction 3, in which you are bifurcating registered and you're writing that both are starting with write, will it not make any conflict?
no, in instruction 3 is not going to write. Instruction 3 is not going to write in the second stage. It's going to read, right? So if it's using that register file, it's going to read, it's using that register file for reading the register, not writing to the registers,
Okay, fine.
right?
Means
So
first half will be empty, the other one will be read.
yes, I'm going to come to that. Why is that? I'm going to come to that shortly when we are going to discuss about data hazards. Okay, so let's take a break, and we are going to come till 7:35.